So hello and welcome back to the video series of finite element analysis. I am Bhavik Soneji and today we are going to solve a problem based on a card system, spring card system. So let's get started. So in the previous video, we have solved one numerical based on the stepped bar. So we will solve the today spring card system problem in the same manner as we have solved earlier. So first of all, let's understand what is the problem statement. The steps remain same. First, we convert the problem into free body diagram. Then we calculate the stiffness element matrix for each element, and then we combine all the elements for global stiffness matrix, and then we solve the problem. So now let's understand first what is problem here. So there are total, as you can see on your screens, there are 4 different springs we have. So this is the assembly of spring, or it is known as spring card system. One end is connected with the fixed end and the other end is provided with the force. The force is applied on the other end. So let's start the solution. So what are the given data? First we will write. So first we have total 4 springs. So first spring stiffness is 4 Newton per mm. K2 second is having 8 Newton per mm. Third spring is having 10 Newton per mm. Same for fourth, K4 20 Newton per mm. And force applied at node number 3. So here you can see there are 4 elements and 3 nodes. So first for data given, the force applied is at node number 3. That's why P3 is equal to 1000 Newton. So these things are given. What we need to find out for solution? So applying this force, we need to find out a deflection or displacement of each spring. So U1, U2, U3 and U4. So now due to this force, there will be some reaction force here. That also we need to find out. So reaction force at the support. So now you are aware about the problem, what we need to do. So now let's start solving this problem. First step is to convert this problem into free body diagram. So let me first show you how to convert. So this is my fixed end. Here you can see there are three nodes. In between there are elements. So in between first and second node, 2 elements. So elements are indicated by circling the number first, second. Third element is in between node number 2 and node number 3. So again, and in between first and third node number first and 3, there will be a element number 4. Now due to the force application, there is a force application here on the node number 3, which is at node number 3. That's why P3 1000 Newton, and due to this force there will be some reaction. on the node number 1, so that is R. So this is my free body diagram. Now I need to uh, do a nodal notations. So first element, second element, third element, and fourth element. So these are the elements, and nodes, corresponding nodes we have to write down. So first element is in between 1 and 2 node. So 1 and 2. Second is in between 2 and 3. Second is in between 1 and 2 again. Third is in between 2 and 3. And fourth is in between 1 and 3. So this is my nodal notation. So in the first step, we have converted into free body diagram and we have given the nodal notation. So now let's solve this problem. So as you know, this is a spring system. So for spring, we know the equation like force is equal to stiffness into displacement. But here we have a system. So instead of force, we have to uh, write the force vector. Instead of stiffness, we will write a stiffness matrix here. And instead of displacement, we have displacement vector. Now, what will be the size of stiffness element matrix? So stiffness element matrix, the size is nothing but 1 into degree of freedom. So here there are degree of freedom. We have 3 nodes, 1, 2 and 3. So 3 degree of freedom, 3 into uh, here number of nodes. So we have 3 nodes and 3 degree of freedom. So the size of stiffness matrix will be 3 cross 3. Now we have to first we will find out the stiffness matrix, global stiffness matrix. So starting from the first element, uh, element stiffness matrix. For element number 1. So K1 equal to, value is given and it is in between node number 1 and node number 2. So first let me write it down. For stiffness element number 1, K1, the value of 1 is 4. That's why K1 into 1 minus 1 minus 1 1. So here the global, it is in between first and second node. So 1 2 1 2. Value, putting the value, K1 into 4 minus 4 minus 4 4. Here we have to keep in mind that it is in between first and second node. Same for element number 2, K2. So value is K2 in putting the value inside 1 minus 1 minus 1 1, putting value inside 8 minus 8 minus 8 8. It is again same in between 1 and 2. Same for element number 3. So for K3, we have value 10. So 10 minus 10 minus 10 10. It is in between second and third node. So 2 and 3 for element number 4, K4. So it will be 20. Value is 20. So 20 minus 20 minus 20 20. It is in between first and third. So 1 3 1 3. Now converting the global stiffness matrix. So capital K global stiffness matrix will be the combination of K1 plus K2 plus K3 plus K4. There will be 3 cross 3 matrix. So first, second and third, 1, 2 and 3. For 1 1 we have 4 plus 8 plus 20. Here you can see 4 plus 8 plus 20. For 2 1 we have minus 4 and minus 8. You can see here minus 4 and minus 8. For 3 1 we have minus 20 only. So minus 20. For 1 2 we have minus 4 minus 8. Same way we have for 2 2, 4 plus 8 plus 10. For 3 2 we have minus 10. Same way we have 1 3 20 minus 10 and 3 3 10 plus 20. So we have now the stiffness matrix, global stiffness matrix in terms of 3 cross 3 matrix, which is having value of this value. So let's calculate that first. So we will have 32 here minus 12 minus 20 minus 12 22 and minus 10, here minus 20 minus 10 and 30. So we have first, second, third row and column. So that will be 3 cross 3 matrix we have. Now for the force vector, we have at the node number 1 there is a reaction force R. So it is denoted by R. At the node number 2 there is no force, so 0, and at the node number 3 we have P3, that is 1000 Newton. Which is having 3 rows and 1 column, so 3 cross 1 here. And for displacement we have same 3 cross 1. So again U1, U2 and U3, we have 3 node, so again it is 3 cross 1. So now for matrix multiplication, we have to do the matrix multiplication. So we can write the force vector F is equal to K into U. Into this matrix U1, U2 and U3. So this is my first equation, which is my main equation to solve the problem. Now as we know that the first node is fixed, now we are applying the boundary condition. First we have converted problem into smaller elements, then we have defined the element stiffness matrix. Now we are applying the boundary condition. So in the first equation we are applying boundary condition. As you know, the node number 1 is fixed, so the u1 will be 0 due to its fixed end. There will be no displacement of node number 1. So we apply elimination method and we eliminate the first row and first column. So we have only two values here remaining. So you can write it down like this: 0,000 is equal to first row and first column we have to eliminate. So 2 cross 2 matrix 22 minus 10 minus 10 30 into u2 into u3. So we have narrowed down the 3 cross 3 matrix into 2 cross 2 matrix. So now converting this into equation form, you can write 22 u2 minus 10 u3 equal to 0, and second we have minus 10 u2 plus 30 u3 equal to 1000. So these two equations we need to solve. So by solving these two equations, we can find the value of u2 and u3. So here you can see we are solving these two equations. We will get value like u1 is 0, u2 we will get 17.85 mm, and u3 we will get 39.28 mm. So this is my first answer, the displacement we wanted to find out. And for reaction we can say first column into first. So R equal to first row into first column, the matrix multiplication. So R is equal to, we have equation 32 u1 minus 12 u2 minus 20 u3. So putting this value in this equation, this will become 0. Here minus 12 into 17.5, and here 20 into 39.28. So we will get R equal to minus 1000 Newton. So this is my answer. So in this way we can find our answers. and R is equal to minus 1000 Newton. So hope you find it useful. Thank you. In the upcoming videos, we will solve uh, one more problem of same kind. Till then, bye.